So welcome to microwave engineering. Today we are going to see about Gunn diode. So microwave active devices. We have different types of microwave active devices. PIN diode, Gunn diode, tapat diode, impact diode. Like that we have different types of diodes. Last class we have seen PIN diode. Today we are going to see about Gunn diode. So Gunn diode is nothing but it is made up of a single piece of n-type semiconductor such as a gallium arsenide or a indium phosphide. So gallium arsenide and some other semiconductor materials have one extra energy band in their electronic band structure instead of having only two energy bands. So which means in PN diode, we have already studied about PN diode. So PN diode having valence band and conduction band. So conduction band. So we have electrons in the valence band. So without any doping or room temperature, the electrons will be at the valence band. If any external bias voltage is given, so the electrons will move from the valence band to the conduction band. So we have only two bands in the case of PN junction diode. As we have seen in PN diode also, PN diode we have three band. So here it is P plus it is heavily doped by the holes and N it is heavily doped and undoped intrinsic material where we have seen the three bands. So like that, so for microwave active devices, considering these diodes, we have one more extra band is called higher energy band. Is called higher energy band. Higher energy band. This is the extra band other than what you have seen we have seen in PN diode. So this is the symbol of Gunn diode, and this is the structure of Gunn diode. So where we have three N layers, there is no P material, only we have N material. So the input side the N material and the output side N material is heavily doped, and we have active N region at the center. So let's we see the operation of Gunn diode. So this is the VI characteristics of Gunn diode. So as we have already seen that so already we have seen so there is a three energy band. So one is the valence band, another one is the conduction band, so another one is the higher energy band. So if the input is so here we will be having the electrons at the valence band. So the electrons will be in the valence band. So if the external voltage is given, if the electron will move from the valence band to the conduction band, so there the current will increase from 0 to some value. So further increasing your external voltage, bias voltage, these electrons from the conduction band will move to the higher energy band. It will move to the higher energy band. So that is the current will attain at that point. Current will attain the maximum point that is called peak point. So if you are further increasing your voltage, what will happen? The electron from the conduction high energy band will jump to the conduction band. So what will happen is the current will start to reduce until to the point value point. So again, once it reaches the value point, it will start to, and again we are increasing the bias voltage. It will start to, the current will start to move from the conduction band to valence band. It will, the curve goes towards maximum operating point. So this region this region is called dynamic dynamic negative resistance region. Dynamic negative resistance region. So where this portion can be used as an oscillator, it will generate microwaves. So that only we are using Gunn diode for high frequency applications. So the here is a few example of Gunn diode. So the Gunn oscillator to generate frequencies ranges from 100 milliwatt to 1 watt, that is 5 gigahertz to 35 gigahertz outputs. And also Gunn oscillators used in radio communications, military and commercial radar sources. And it is used as a sensors for uh, detecting repasses to avoid derailment of trains. And also efficient microwave generators with frequency range of up to hundreds of gigahertz. And it uses remote vibration detectors and rotational speed measuring tachometers, and also it uses microwave current generator. So these are the few examples of Gunn diodes. So normal PN diode we are not able to use for high frequency applications because the reverse recovery time in PN diode is large. So we need switching of the diode should be very high, but in case of PN diode it is low, and capacitance is a low capacitance in the PIN diode. Normal PN diode it has higher capacitance. So if you have a higher capacitance, the switching time will be more. We can't use it for high frequency. So in the case of high frequency applications, the switching time should be low. So if you take PIN diode, it has a low, the switching frequency is high, but in PN diode the switching frequency is low. That is why PN diode is not used for high frequency applications. Thank you.